Hi, this is how to measure jitter in eye diagrams, and my name is Carolina Gomez. In this video, we will cover LVDS, our lab setup, eye diagram configurations, jitter measurement, and the trade-off between different cable lengths and data rates. Low voltage differential signaling, or LVDS technology, connects a driver and a receiver together with a differential pair that is closely coupled. When external noise is present in the environment, both wires will receive nearly equal amount of noise. Since the receiver only cares about the voltage potential between the two wires, the external noise will be canceled. LVDS is also low cost, low power, has small packages available, and a simple implementation requiring a 100 ohm termination between the driver and the receiver on the differential pair. Using the DS90 LV04748A evaluation module board, which connects the DS90 LV047A LVDS transmitter to the DS90 LV048A LVDS receiver. As you can see, these parts are 4-channel parts, but in this example, we are only using 1 channel. In this lab setup, a pseudo-random binary sequence, which is commonly known as a PRBS, is sent in and passes through the differential pairs between the driver and the receiver connected with a Cat5e UTP cable through the receiver and out into an oscilloscope. The signal seen in the oscilloscope will be changed from a PRBS to an eye diagram in the following steps. First, let's talk about eye diagrams. They are made from a signal being repeatedly sampled on top of itself. In a theoretical world, eye diagrams would look perfectly square. But because of rise and fall times, the output turns into an eye. The best time to sample is in the middle of the eye, where it is the most open and there is no jitter. Jitter is the time difference at the crossing lines of the bits. The PRBS is shown in the oscilloscope from the output of the receiver. To have a signal sample over itself, persistent mode must be turned on. This can be done through the display settings, in which the display persistence is turned on indefinitely. To have an image hold still to make measurements, in advanced trigger settings, select Communications Trigger in order to generate an eye diagram. The level of trigger should be placed at the halfway point of your signal. So now, you just have to zoom in to where the two bits meet. Using the cursors, I get a time difference of about 272 picoseconds. To get a more precise reading, I create a histogram with a 50 millivolt voltage difference that goes across the cross-section. Selecting to see the horizontal peak-to-peak measurement of the box enclosed, it tells me that the actual jitter is 284 picoseconds. This can be repeated for any data rate or cable length. At different cable lengths and data rates, the jitter changes. This is important when choosing which device fits best within your design. For example, a 1 meter cable with 400 megabits per second data rate has a jitter of 290 picoseconds. This means that in a period of 2.5 nanoseconds, 290 picoseconds of that time is unmeasurable for a clear reading, which is 11.6% of that time. This is an acceptable amount of jitter for the typical application of a multifunction printer. So let's review. Why do we use LVDS technology in this jitter measurement example? A single-ended signal is less susceptible to common mode noise. Or B, a closely coupled differential pair is less susceptible to common mode noise. The correct answer is B. A closely coupled differential pair is less susceptible to common mode noise. At higher cable lengths and data rates, the jitter percentage should A, increase, or B, decrease. The correct answer is A. The jitter percentage should increase at higher cable lengths and data rates. Thank you for watching this video. For more information about Texas Instruments LVDS receivers and transmitters, please visit our portfolio. Watch the LVDS training series, or ask a question on our TI EDE community. Have a great day.